The play on words everyone might not have caught was there's a recent Wired magazine article about our device, and they coined the phrase wonder buoy from I believe, an earlier publication. We do not yet have a name for the device. We're still looking at different options for trademarks. So I'm here to talk about wave power at the utility scale, or more specifically, high efficiency wave power. Guess I'll grab my clicker. We're a wave energy company based in Stockholm. However, if you may not have guessed already from my unique accent, I'm not actually from Sweden. I spent a little more than 15 years here in the US defense industry, working primarily with power systems, and then kind of decided to try something different and moved to Europe, where I could help advance wave power at the epicenter of the current development. A few people have already spoken today about the huge untapped resource that relies in the oceans. I'd like to add real quick that it's reliable, consistent, and highly predictable, and is 5 times more energy dense than solar and 10 times more energy dense than wind. Which, when you add all that together and put it in reference, the potential for wave energy is about 4 times the global installed nuclear capacity in the world today. Here in the US, that potential is, of a similar mix, which equates to an enormous market potential, while also directly aligning with the Paris Accords and other climate change plans that we are now a party to. I'd like to add, too, I spent the last week or so taking some meetings and giving a few presentations in both Washington, D.C. and San Diego, and was really quite impressed and surprised by the growing interest in commercial scale wave energy that we're seeing now in the U.S. Also very important, you can say that wave energy directly aligns with 12 of the 17 UN global goals for sustainable development. There we go. The real challenge for the future of renewable energies is to continue to provide that cheap source of reliable energy as we switch to more sustainable sources. And in wave power, this manifests itself in a unique challenge of designing devices that are robust enough to survive the most difficult storms, while also being efficient enough to provide a competitive return on return on investment, And so far what we've seen is this difficult requirement to survive storms has driven devices to be, very, very large and very costly. And when you get that big, it becomes very difficult to maintain the cost competitiveness that's required. However, this is something we're aiming to change. Oh, there you go. What we've seen so far with devices that have been tested in the ocean is around 1 to 1.5 megawatt hours per ton of device. And I'll say briefly, we use, and it's becoming a more common standard in the industry, to use this megawatt hour per ton as a structural efficiency metric to use, because it removes a lot of the assumptions that come with cost projections in such an early stage of development. But when you compare this to modern wind turbines, they're close to 10 megawatt hours per ton in structural efficiency. So you can see that in wave power, we do need a step change in this efficiency in order to be cost competitive. And that's kind of specifically what we've targeted to look at. At CorPower, we've developed a compact, high-efficiency wave energy converter that was initially inspired by the pumping principles of the heart. We have 3 core patented technologies, being the pre-tensioning system, the high-efficiency gearbox that's now been commercialized under a sister company, and the phase control that we've coined WaveSpring. And I think the WaveSpring is more what I'll talk about today, because this is what allows us to maintain resonance with the incoming waves, which we do feel is vital for the future of wave power. And with this WaveSpring, we're able to attain and maintain this resonant effect with all incoming waves, no matter of the timing between waves or the direction of the waves, which then strongly amplifies the motion of the device, which then gives it its greater power output. I mentioned oscillating and resonance with incoming waves, which could be a mouthful for folks who aren't familiar with the industry. So I'd like to present an analogy that we see sometimes in the industry, basically being a child on a swing. If you want to provide the optimal amount of energy transfer between the parent pushing the child and the child, you put yourself in the right position behind them, and you push at the peak of the backswing so that you're not counteracting their backward momentum with your pushing force, and you're not pushing too late and essentially chasing them. And you create a positive feedback loop that then makes the child go higher and higher with each swing. When we relate this back to wave power, anything floating has a natural period of oscillation or a natural timing with which it bobs in the water, and that's determined by just the hydrodynamics of the device. So what we look to do is, if you can have your device naturally on its upswing, at the same time you get the lifting force from the incoming wave, and similarly the device wants to restore itself to a lower position naturally, at the same time that the wave rolls away, you get this positive feedback loop, and the device can literally jump in and out of the water, giving you this greatly exaggerated linear motion that you then convert to energy. And as I mentioned, with the wave spring, we're able to synchronize and maintain this resonant effect for all sea states. It's a quick video to show a little bit about our device with the pre-tensioning module and this wave spring phase control. Here's a video of our tank testing we did a while back, and you can see with the videos the difference between the device that's jumping in and out of the water with the phase control system turned on and the one that's not moving nearly as much with the phase control turned off. And that's also important because that gives us our storm survivability. It's a passive device that naturally synchronizes, but we can turn it off. So therefore, when the waves get beyond a comfortable level for the device, similar to how wind turbines pitch back into the wind, you can detune this device, remove the resonant effect, and greatly lower your efficiency and therefore lower the loading on your device and make it much more survivable. A quick timeline just to show that developing our technology to this maturity has not been a simple or quick process. It's been a common pitfall in the industry to build very big very early and not quite understand the behavior of the device, and then to ultimately not be successful. We've avoided this by taking a structured approach with extensive testing at the smaller scales. We're currently working with the European Marine Energy Center, Wave Energy Scotland, and the U.S. Department of Energy National Renewable Energies Laboratory to do technology assessments as we progress towards commercialization to make sure we identify areas where we can continue to improve our efficiency. The company was actually founded in 2009, which is a bit off of this chart because the first couple years were simple concept validation, and in 2012 the validation testing started in earnest. We did tank testing at the 1/30th and the 1/16th scale in France and Portugal, and upon positive results from that we moved on to a third scale test lab in Stockholm at the KTH Royal Institute of Technology, and that lab has been operating for 2 years, supplying to the Swedish grid. We're now currently in development of our half-scale ocean prototype that is being built currently and will be in the water next year in 2017. And that would then put us on a path for a pre-commercial pilot farm, the 2018-2019 timescale, with the potential for a commercial plant in 2021 or even 2020. It's a quick video of our third scale lab in Stockholm. It may be hard to understand here, but the black box that you can see on your right is a motor that simulates wave motion through software we developed that's then connected to the linear rod through a cable and pulley system under the floor. And the white box on the other side is our patented high-efficiency gearbox that then translates this to rotational motion and then to electricity. Just a quick picture of the tank testing we did in Portugal, I believe this was. And the important part to notice here is that, or to mention here, is that we've now had the opportunity to calibrate our numerical models with 3 separate sets of results and have been able to show less than 10% variability between our numerical models and our actual results, which we expect to continue once we hit the ocean. Also important, now that we've had the opportunity to calibrate this model over 3 test periods, we have shown our device on a path to 3 times more energy per drivetrain force and more than 5 times more energy per ton than what I had mentioned earlier as a state-of-the-art, which then puts us on a path to compete with the structural efficiency of modern wind turbines. And to characterize this a bit, there's a recent publication by the University of Edinburgh that looked at a few different wave energy devices and singled out CorPower as on a path to, I believe they mentioned 14 cents per kilowatt hour after 100 megawatts of installed capacity, which puts us, on the doorstep. And to characterize a little bit about wind, since I do mention that as a target that we aim for as far as structural efficiency, you can see here the dramatic decrease in the cost of energy of wind with the recent exponential increase in installed capacity. And I think wind today is somewhere between 4 and 9 cents per kilowatt hour and even cheaper than natural gas. We chose the EMEC test site for our current pilot that we're doing in partnership with Iberdrola, a Spanish utility company, among several other partners, because in northern Scotland they not only have a great wave condition, but they've been an operating test site for more than 10 years, and therefore have worked with more developers than anyone else. An additional key aspect to this test program, we're building a full system test rig. We'll be able to take the entire device, turn it sideways, and exercise it in full storm conditions in a controlled environment in a test lab before we go out to the ocean. We'll also be able to recreate events we see in the ocean and make sure we're able to fully characterize and understand the device. It was an amazing experience this past year with this half-scale device. We design locked the final design, detailed design in May, now have the composite buoy delivered to Stockholm, are in the process of module testing and unit assembly and expect to start full-scale testing by the end of the year. Our go-to-market strategy, I think, is similar to many developers, where we focus on our core strength, being the intellectual property of those 3 patents that we have in the internal conversion chain, and we can partner with, similar to how we've done with Iberdrola, and we have an upcoming program where we're in partnership with EDP, a Portuguese utility company, and leverage on their extensive experience in infrastructure and large systems integration. Obviously, waves are a global resource, so we need to focus our efforts. You can see in brown the enormous resource around the world. We've determined to stay in Europe for the near term because that's where our existing funding and our existing partnerships are. And also we found that to be the best opportunity from terms of access to sites, legal and consenting, and just the demand for wave energy. But we do see in the mid to long term an increasing need around the world and a very much increasing interest around the world. Just to look at the team driving this innovation to market, we have a very diverse team. Some of the best-known scientific and academic minds in the industry started this team, and we've now balanced that out with a bit more folks with experience as far as previous successful startups, legal, contracts, business development, and project management in larger established industries. The folks across the top, I would mention, have raised for previous companies more than 100 million in startup capital, more than 20 patents, and if we include our lead scientist, who's not shown, I would say close to 50 scientific publications. We've also recently added Anders Jansen, who some may remember was a previous Orcel Award winner when he presented here as a CEO of Monesto, who he took that company to successful IPO and then gave it to a more commercial CEO and decided to look for his next entrepreneurial challenge, which we are happy to take on board. However, most importantly, at CorPower, we take great pride in attracting top quality talent from around the world in various backgrounds. And we felt when doing something this new and groundbreaking, it was quite important to be able to pick from different experiences and different backgrounds. Currently, CorPower is 21 full-time staff and represents 11 nationalities across 3 continents and speaks 14 languages. We have folks from backgrounds such as wind, tidal, oil and gas, automotive, aerospace, and defense. What we would do if we win, currently we're testing in Scotland for 6 months. That's what we have funded and scheduled so far. An ocean exchange award would allow us to double this test period and to be able to stay in the ocean in Scotland for a full calendar year, which would then give us data during all 4 seasons, and most importantly, give us, even more so than understanding the performance of the device, we would then be able to have that additional time to fully understand all the operational and offshore aspects, as well as winter storm survivability. And I do believe all of these are vital in order to live up to the Wired magazine article that did identify CorPower specifically as providing the step change in efficiency that's needed to bring the industry to commercialization. So I believe my time's about up, and I think I'm about exactly done, so that works. Thank you very much.
Daniel, really good. Great stuff. So as people are coming up with questions, I have one.
Sure.
So for storm survivability, you have a tether. Is it feasible to have a tether that would pull it down under the water?
We have looked at that, and I think that's something that as we go bigger, we may look at more. The difficulty is, I mean, you don't need to pull it down all that far.
No.
You do have to then withstand the additional loading on the structure. For our half-scale deployment, when we decided to look at this, it was a bit late in the process, and the structure wasn't designed to handle that. Yeah. So we've discussed it, and we do think currently the models show that just by taking the device out of the resonance period, yes, we have enough storm survivability, and we're able to continue to produce.
Great.
But we have in the background looked at that as another option.
So who's got a question? One's coming over here.
I see movement.
And another. You were here first.
Buzz Kirk. It's interesting, the shape. What drives the shape and the volume that for your?
It's really hydrodynamics, and I guess I glossed over, forgot to mention, the full-scale device is an 8-meter diameter buoy at about 280 kilowatts, and we chose that small size to optimize the hydrodynamics of the device, but then also to make it a bit more handleable for offshore logistics, and to provide this efficiency, like we were saying. If you were to look at, a megawatt, we would have 4 devices, which would be about, at 75 tons each, maybe 300 tons of device, which is still, quite a bit smaller than what you would see for devices of that size. But I guess I veered off topic a little bit. It is purely the hydrodynamics that is the design method behind the device.
Is it steel on the outside? Is that to provide a weight? I mean, is that all part of it?
Yes, it's the outside is free floating. The inside is what's attached to the tether and maintained tensioned against the seafloor. So it's the relative motion between the inner power conversion train that's attached to the seafloor and the outside free-floating buoy. So it does seal against the bottom rod.
We're here.
Good, thank you. So you project to be at 14 cents a kilowatt hour?
That was done by University of Edinburgh. We provided them with data.
Right. And so where do you see this, or how do you get to 4 cents a kilowatt hour to be competitive, say, with wind? Mm-hmm. Is it a technology advancement? Is it a scale factor? What is going to get you to that lower cost? I think you have tremendous advantage over wind, mm-hmm, especially here in the U.S., where there's a huge, aesthetic opposition to offshore wind. And I think, having these buoys out there, I don't think is going to offend
exactly,
people that own shorefront property. But how do you get to that, to that next level of performance?
I would say primarily supply chain. That 14 cents per kilowatt hour was projected based on 100 megawatts of installed capacity. And when you look at wind, I think 63,000 megawatts were installed just last year. So once you're able to kind of develop the supply chain and have those types of numbers of devices, then all your logistics get much cheaper. Sure.
That epibiota with the on the line and on the buoy itself.
We have, as part of this half scale, we're testing a few different materials to look at. We're in partnership with 2 different universities to look at the best way to do that, or the best way to approach that. And we'll get a lot of data offshore with that this time. The other part of that too is we've incorporated in the full-scale device mooring line quick disconnect. And because these devices are so small and lightweight, they're relatively cost effective to tow to shore. And we've been talking to a few partners about the potential of modifying large boat trailers to even take them up slipways. So the idea is that there is a lot of motion in the device. So if we could get it to where you only need to truly clean that every 5 or 10 years, then you could do that with maintenance periods. I mean, I understand what you're saying. That's not a near-term thing, but these are things we're looking at for the longer term.
Jeff?
So I always try to come up with something a little different in
Sure.
the questions, but this is sort of like the 100-year wave question. And it goes to not just in your particular technology or product, but several of the others that we've heard that are basically floating around or semi-submerged in water somewhere. And so the question is when, and it's not when, or it's not even an if, it's it will break free and one will escape. And is there a tracking recovery system? I mean, yours are pretty big, but when you're looking at storm conditions and something that's painted a sort of a dark color, at least the current, or not like bright, green or something, do you have a system like an EPIRG you have on a diver or emergency raft or rescue vessel that allows you to track, find, and then easily recover it at sea? Because yours is small in the world of wave power,
But it's still
But
quite
it's
large.
big when it's
Yes.
hit by something. So-
Absolutely, absolutely. No, and I think you're right. I think they say the definition of the 50-year storm is the storm you get 3 months after you install. So I mean, you have to plan for things happening that you don't want and have designed to try to avoid. And we do have, as part of our requirements for the deployment, we have the big yellow top, and there is GPS tracking in it that does same as you would have with navigational boats. And we're currently in the consenting process with Marine Scotland, so we're working with them to identify exactly the devices that we need. And we do have, with the size of device we have, it is recoverable by a larger range of ocean vessels. You don't need really specific vessels to go out and get it. That's the best answer I have at this point, but I'm sure we'll learn a lot over the next year.
Daniel, great job. Thank you very much.
Thank you. I appreciate it.